Hey, I'm Andrew Sallee, a second-year graduate student in Dr. Rule Tomflar's group. When materials get really thin, they can start behaving differently than they do in bulk. My research is on single-layer transition metal DICHALCOGENIDES, or TMDs for simplicity. From their name, these TMDs consist of a transition metal and two chalcogens, which is a fancy word for group 16 elements. Specifically, the TMDs that I'm interested in consist of tungsten, or molybdenum, and two sulfurs, or selenium. These TMDs exhibit very interesting electronic properties that we would do well to take advantage of. Specifically, I'm interested in how these TMDs behave if we put them in a small crevice and then shine light on them. When I say really small, I mean really small. These TMDs are only 3 atoms wide, and the holes that they're in, nanometers in width. When we get to this scale, quantum mechanics plays a role. Why would this be the case? Well, quantum mechanics, that is, the physics that things appear in countable units, becomes very prevalent and very important at these small scales. For example, you could have 1 electron, 2 electrons, but not 1.5 electrons. That said, when things are large, they behave as though this is not the case. When we get small, these units start to matter. Fortunately for TMDs, we are at the atomic scale, which means that we can take advantage of quantum mechanics predictions. When you excite these TMDs with light, wave particle duality, one of my favorite phrases, comes into play. What is this? In essence, the single units of stuff the universe is made out of act as though they were spread out over space, much as ripples in a pond are. That is the wave nature. But, as I earlier said, they are single units that can move around and do things. That is the particle nature. These wave particles can also interact with each other to create hybrid wave particles. For example, with these TMDs, the photons and electrons that we're dealing with can interact with each other to create a single sort of particle that actually is the system of interest. How do we know this? Well, making certain assumptions. We set up what is called the Schrödinger wave equation and politely ask the computer to approximate a solution. If we do this correctly, the computer obliges and we get a nice result. Unlike with a simpler system such as a hydrogen atom, we can't actually write out this result as an analytic equation. However, like with the hydrogen atom, these solutions have certain energies that we can figure out associated with certain probability distributions. When you get these TMDs with light when they're by themselves, their excited states look a lot like atomic orbitals, and so they get names like 1s, 2p, and so on. If we put these TMDs in a hole first and then shine light on them, those things indicate a probability distribution of different excited states, so typically 1 or 2 predominates. Depending on the structure of these holes, energies become shifted from where they would be if the TMD was all by itself. This means that we can take the energies that we start with and shift them around, separating ones that were at the same energy from one another. This all might sound pretty abstract, but here's an example of how this can be important. TMDs naturally have states that act the same with regards to energy, but act differently in other regards. Naturally, typically when you produce these states, you get both. You get a combination of them, which is not what we want often. If we want to isolate one of these specific states, we need to make them act differently with regards to energy first, and then we can isolate the behavior that we want. By knowing how these TMDs behave in tiny crevices, we can engineer similar environments and all sorts of electronics, giving us greater control at the quantum level. These TMDs could act in efficient solar cells, or as the semiconductors in computers, to great effect. Being a researcher is kind of like being a detective, with a lot of leads, many of which don't make sense. But through a lot of hard work, you can piece together a compelling narrative. At Northwestern and beyond, there's all sorts of groups that are looking to train undergraduates of various backgrounds to work on the problems of our era.
Thank you for watching this Chemistry Research Connection video. My name is John, and I'm a 4th-year graduate student in the Department of Chemistry at Northwestern. I know the pandemic has left us all feeling very uncertain about our futures. But I want to remind you that even in these times, Northwestern has a wide variety of opportunities for you to get involved in research. No matter your background, major, schedule, location, anyone can get involved with research. All it takes is interest. So, if you are interested, please check out this link above. Thanks again for watching, and stay healthy.